trade my soul for a wish. Pennies and
Stop,
dimes for a
Beyonce.
kiss. I wasn't looking for.
Get off of my computer. All right, I was having a little technical problem here. It's the first time I've used this software. So apparently there's a recording limit of approximately 15 minutes. So we can wrap this problem up, and I can talk about this some more when I'm back. But let's make something clear right here. What makes all these, this point right here, equidistant from all of these? Well, when we draw this in, it's equidistant from these two because it's on line L, and it's equidistant from these two here because it's on line M. Then that makes all three of them equal through a little application of substitution or transitive property, and I can go through that on Monday if you wish. Now we have the angle bisector theorem. If a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. If point S is on the angle bisector of angle PQR, then SP, this piece right here, is equal to this piece right here, the piece that looks like it should be equal to. SP is equal to SR, which means the distance from S to P is equal to the distance from S to R. Now the converse is also true, which works the other way. If we have an angle and we have a point that's equidistant, then the point in question must lie on the angle bisector. I'll put the arcs in to show you that they're equal. I don't know why there's not angle bisector marks up there. I guess I'll go add them. Now, the big question here is, and I know people have asked me in the past when I've talked about this, why do I keep putting those little boxes there? Well, the reason is we always measure distance straight up and down. If you think about it, you're standing there doing your thing, and your friend comes along and wants to measure you. They get out a measuring tape and they measure straight up on a perpendicular to the ground. They do not put the measuring tape over here and measure over to your head like that. That would not be your correct height. We always measure the shortest distance. And the shortest distance up here in all of these cases is on the perpendicular. So let's see, point S is on the interior of PQR if, and that's this if right here, if SP equals SR, then S is on the bisector. Okay, and it has got the theorem and its converse, so it goes both ways. It's an if and only if. Let's apply it, and this is a very typical problem right here. What is the length of FB? What is this length right here? Well, let's look at what we have here. We have angle BCD, and if you look at the arcs, we've got 1 and 1. So CF, ray CF, is a bisector. And what does that mean? It means that any point on CF will be the same distance from the two sides of the angle. So there's our point. These have to be the same. Now what makes them the same? They're measured on the perpendicular. If we had this drawing, sooner or later you'll get one of these, like this, and the bisector was drawn in, like there, we know it's a bisector, and these lines are on here like this, but wait a minute, where's my little perpendicular box that I expect to see there? If that's not there, then we can't say these measurements are equal. That is a strict requirement. We need that little box there to show us these are perpendicular, to show that we're measuring on the shortest path. Otherwise, how do we know this person isn't measuring way over to there? to find the distance. And that is obviously wrong. So because of the little marks, the boxes that say they're perpendicular and the little hash marks that say they're equal, we know these two are going to be equal. So FB equals FD, that is given, which is basically means it's in the drawing. Okay, now we're going to substitute these in. Sub in from the drawing. FB is equal to 6x plus 3, and FD is equal to 4x plus 9. We know they're congruent to each other. Oh, I don't like the way they do things, but I guess I'll follow along. Minus 3 to clean that up. And we call this we'll just call it subtraction. We don't need to dwell on the finer points of that for now. And now the next step is minus 4x. That will cancel. And we'll have 2x equals 6. That's subtraction again. Now we're going to divide by 2. That's good old division. It's actually the law of algebraic equality of division or some such thing that doesn't concern you. All right, so x equals 3. But is that what it's asking? Let's look up here. No, it wants the length of FB. Well, FB is 6x plus 3. You're going to put 3 in right there. 6 times 3, 18, plus 3 is 21. So we're going to sub into the original and then compute FB. And there you go. There's a whole bunch of those on the practice G. We'll be doing the evens. I'll try to get the key up as soon as I can, probably sometime Friday morning. All right, use the figure at the right. What is the relationship between AC and BD? Let's look at this. Underline the correct word or symbol to complete each sentence. AC, hold on, I gotta pause. Go ahead, ma'am. Okay, sorry, we had some people working in the school tonight. All right, AC is either parallel or perpendicular to BD. Well, let's look. AC and BD are certainly not parallel because they intersect right there at E. So they are perpendicular. All right, sorry about that. I had to pause for a minute for the cleaning staff to vacuum. So we were talking about AC is perpendicular to DB. AC divides DB into, it looks like, because of these little marks, two congruent segments. BD divides AC into, well, there's no markers here. So the only thing we can go with is that they are non-congruent segments. I mean, they could be congruent, we really don't know. We're just going to leave that alone for now. Finally, AC or BD is the perpendicular bisector of which one is which? Well, I would say that AC bisects DB. AC bisects, well, it's BD, but DB, BD, same thing. What are the 15 and the 18 for? Well, we'll do stuff with those down the road. This is a quadrilateral. It's a polygon that's called a kite. And we're going to learn about the behaviors of the diagonals of this kite and how to classify that when we study polygons in a couple of chapters. So we'll be coming back to that thing. You see there's a big green kite hanging up on the board up there. Now, if you'd like to stop and review, maybe you can write down what you know about these things before I define them for you. Rate yourself here. I'm going to give myself a 10. I think I get it. All right, so if you want to pause, do so now. Otherwise, perpendicular bisector. What is a perpendicular bisector? Anybody? Just kidding. Perpendicular bisector intersects a segment at a right angle and bisects it. So you got a segment like this. It's going to go right through the middle at a 90-degree angle, and those two pieces are going to be equal. Next one is equidistant. That should be pretty easy. Equa. That means same distance. What does it mean, especially in regard to what we're talking about today? Down here, every point on the perpendicular bisector is equidistant from the ends of this thing. You pick any point on that perpendicular bisector and it will be equidistant from the ends. Also, when you bisect an angle, every point on this bisector right here is equidistant as measured on the perpendicular. So there's equidistant. Last, distance from a point to a line. The distance from a point to a line, take any point out here, it is always on the perpendicular. Once you have that perpendicular, any other line, by definition, is farther. We do not use those. That's not how we measure. You don't hold the measuring tape up to your head and throw the measuring tape across the room and say, I'm 14 feet tall. No, you measure straight down to the ground. That's how all measurements will be done. All right, I hope this works out for you. We are going to do the practice G, and we will do the evens. I will have the answer key up as soon as possible, including these notes and this video on Schoology. I may have to put this on YouTube. Hope you have a nice weekend and get ready for homecoming and Spirit Week. Thanks.